So in this lecture, we're going to add a single letter to ANOVA, and that is covariance, the analysis of covariance. So ANCOVA. So we're going to be introducing ANCOVA and then specifically spending a lot of time on computing ANCOVA when we're using it to do a blocking variable. So before we even get into the lecture, I kind of want to go over this a little bit because if what we're using for the idea of covariance, covariance means that there is a variable that we have measured that we expect to be related to our outcome, but we are not interested in as far as theory or hypothesis. In other words, it's a variable that we think is going to get in the way or create noise, but we're actually not concerned with. So for example, if what we're really concerned with is whether a treatment overall has an improvement on an outcome, but we know that the outcome is affected by gender. So men and women differ in how they actually score on that outcome. If we didn't measure gender, we may have an issue with gender. Now, this is different than if we were matching. We're not matching on gender. We're simply measuring it and telling the analysis of variance, remove any variance we find based on gender before you look at the relationship between our treatment and our outcome. So this would be an example of when we'd run a covariate. Now, if the covariate is continuous, if the covariate is a measure that is continuous or on ratio data, so if it's a personality variable, if it's a test score, if it's a pretest, at that point, all we're doing is running an analysis of covariance. We really don't have to do anything else. We can simply put that variable in as a covariate. However, we may actually be more interested in a categorical variable. And if we're doing a categorical variable, or what we're interested in is categories, that's when we need to do a little bit of work beforehand to create a blocking variable. And again, a blocking variable simply means that there is a categorical variable that we think is going to be potentially related to our outcome that we're not interested in. We don't have hypotheses about it. We don't have theory about it. We basically just want to get rid of that difference. A good example of a blocking variable, therefore, might be if you did your study at 3 separate schools, those schools may have variance. In other words, each school may have different performance levels and different types of students. But you're not interested in the differences between the schools. What you're interested in is if your intervention worked at all 3 schools, at least to some degree. And if you didn't account for the differences in the school, that might actually blind you from finding the results you're interested in doing. So in this case, we would use a blocking variable. We'd add an ANCOVA based on the idea of we want to take a categorical variable, the blocks, the 3 schools, and account for that and remove that variance before we looked at the actual true effect of our intervention on our outcome. Now again, the biggest thing to recognize here is that the decision to use a covariate is based on theory and hypothesis. If you have a theoretical reason to look at a variable, and if you have a hypothesis about how you expect that variable to function, you're not doing covariance. It's not a covariate. It's a independent variable. It's only when we have a variable that we have information on, we've collected data on, or we're purposely measuring, that we do not have a hypothesis or theory around, but we do expect it to be related to the outcome, and that we want to account for those differences before we actually look at what we're caring about, our hypotheses and our theory. So our introduction to the ANCOVA. ANCOVA adds a covariate to the model and the purpose of this is to extract extra variance from the treatment effects. Basically what we're hoping to do is to find variance that is unique between the outcome and the covariate that actually reduces the amount of error. And by reducing the error, lets us focus better on the actual outcome. In other words, we're basically measuring error to hopefully remove it. And when we remove that variance, we're treating the covariate as noise. We're not treating it as something we care about. We're not actually creating hypotheses on. Even if it's significant, that simply means that it probably was a significant predictor of the outcome, which means it's probably worth removing. The only way to know if a covariate really is helping is to look at running ANOVA without the covariate and then run the ANOVA with the covariate. If you find that the ANOVA has a stronger relationship, a stronger effect size, and is basically less likely due to chance, in other words, a smaller p-value, that means the covariate is worth it. If you run an analysis of variance and then run a covariate and find that the model actually gets worse, a smaller effect size, a smaller f, and a larger p-value, at that point the covariate is probably either unrelated, isn't affecting error or may even be related to your independent variable. Now again, generally if we're going to add covariates, we do want some theory behind them. That they're not atheoretical. They're just not a theory that we're interested in researching, and it's not a theory that's the focus of our hypotheses. We're often going to use theory to determine what covariates would we expect to be related to our outcome so that we can measure them to include them as covariates. And the purpose in this is to give a clearer relationship between our outcome and the predictors of interest that we care about, those that we've created hypotheses for. So the within-group variance is reduced by accounting for the relationship between the covariate and the outcome variable before we look at the relationship between the predictors and the outcome variable. And like I said, there's basically two broad types of covariates: categorical covariates, which is often referred to as blocking, and continuous covariates, which is basically effectively we're doing a brief multiple regression prior to the ANOVA to account for that error variance. And again, I really want to focus on that idea that the difference between a covariate and a predictor is mathematically not really different. In other words, they're variables. But what we're wanting to look at and how we're treating them based on our methodology and our theory is what changes. So not all extra variance should be removed. Not all variables should be treated as covariates. An alternate is to examine those differences between those extra factors through a factorial ANOVA or a multiple regression. So like I said, before we decide on a covariate, we have to make sure that A, it's related to our outcome, basically based on past theory, or at least is potentially related to our outcome, and B, is not something that we're actually interested in. We have no hypotheses about it. We're really just interested in removing that effect. And usually, theoretically, we're interested in removing that effect because we're not interested in the difference between how an intervention worked at school 1, school 2, and school 3. What we're interested in, did that intervention work to some degree at all 3 schools? This can commonly also be used to adjust for pretest scores or known biases. So for example, if I'm doing a study where I know there's pretty big differences based on your age and how you actually look at outcomes, that might be a good time to put in a covariate. If I have any isms, so if I'm looking at, for example, how people react to applicants in a job interview based on their demographic categories. If I'm looking at the demographic differences of how they rated males versus females, I might want to measure basically sexism. So again, do I find that there's a difference regardless of whether you think you're a sexist or whether you report that you're a sexist or not? GPA might be an example if I'm looking at an intervention. So again, I might want to adjust for GPA. In other words, yes, my intervention might work better for people with higher GPAs, but I want to adjust first for GPA because I want to ask the question, does my intervention work for you regardless of your GPA? SAT would be another example. So blocking is simply a method for covariate adjustment that removes variability from the error term, hopefully, by controlling for a categorical variable that may influence the outcome. The procedure is much like matching, but the units are matched by categories or groups, and we're not actually specifically going through the process of matching people one-on-one. We're simply actually using the measurement of what might be used to match people to basically treat it as a covariate. So this is a very easy way to kind of address this issue. So for example, we might block people by their gender, so compare males and females, but again, we're not comparing. We're simply saying we're not interested in gender differences. We expect them to be there. We want to get rid of it to ask, beyond gender differences, do we still find this main effect? Might be percentile groups, so high versus low performers. And the idea is that the blocking variable, the categorical covariate, will change the estimate, the F ratio, by reducing the amount of error. In other words, it's going to account for some of the outcome variable, but hopefully it's also going to account for error, and we can remove both of those. Now, if you think about this theoretically, if you've got a covariate that's associated with both your outcome and your predictor, and especially if it's effectively equally related to both, it's going to basically pull out variance from both the effect and the error. That's why we really want to find variables that are related not to our other predictors, but are related to our outcome. Because they'll reduce potentially some of the variance that's being explained by our outcome, but it shouldn't reduce the variance that's being explained by our predictors if it isn't related to our predictors. But because it's reducing some of the actual unexplained variance in our outcome, it will also reduce some of the error. So just some quick examples of blocking. We might have a control versus treatment, and we're looking at basically coffee consumption. And we might know from previous research that there is a difference between the two programs. Now, one way we could handle this is instead of blocking with a covariate, we could actually try to match. In other words, we could match data. We want to look at similar students. So for example, we might match two clinical students from two different years, two other clinical students from other years. Except when we're matching, we have to ask ourselves, are we really matching? Because if we're doing a matching, if we're basically moving to a within subject design, what we are saying is that by measuring what program you're in, Lisa is the exact same as Anne, that Maddie is the exact same as Pat, and Ramar is exactly the same as Kathy. That is a hard argument methodologically to make. That's where covariate blocking can be a much more useful tool. We're not claiming that Ramar and Kathy are the same. We're simply saying that whatever variance is there, because of whether you're in clinical or IO on coffee consumption at any time, we're going to remove that first. We're not going to have to necessarily worry about the differences between clinical in general and IO in general in how they drink coffee. Now, if we're using continuous data to do blocking, in other words, we're not treating it as a continuous variable, we're using that continuous variable to look at groups or categories, the values of the covariate are then divided into intervals so that each block has a group of treatment and control participants. So generally speaking, if you're going to break up continuous data, what has been found is that the most effective number is 5. Now, this is a rule of thumb. It may change from variable to variable, but Cochrane did a fairly large study in 1965 where he basically did Monte Carlo simulations, which means he was using fake data, but he was looking to see, just broadly speaking, if you took any continuous variable that had an outcome, a relationship with an outcome that could be used as a covariate, and you then created blocks with it, what were the most effective number of blocks to create? 2, 3, 4, 5, 6, 7, etc. He found that generally 5 blocks were a good way to actually account for data and let you focus more on what you're interested in, the predictor and the outcome. So again, the treated and control units should be comparable within each block. What that basically means is that if you create a block, let's say that we're using SAT, and you break it into 5 categories, very low, low, moderate, high, and very high. If you find that in the very high condition, you only have people in the treatment group and no one in the very high condition is in the control group, that's not going to be very helpful. You're probably going to create more problems than you solve. So the line treatment and control units should be comparable within each block, means that once you actually do a blocking variable, once you actually break up a continuous variable into blocks, you want to make sure that within each block there's roughly the same number of participants in your other conditions, basically your other IVs. Unlike matching, blocking usually permits the inclusion of all cases. So this is one of the advantages also of blocking, is you're not going to necessarily lose data. And also, you're not making the statement that the people in each block are identical. You're simply saying that you're accounting for the difference in the blocks before you look at the primary hypothesized relationships between your predictors and your outcomes. Blocks can have unequal sample size, especially between each condition for the blocks. Changing the cut points that define the blocks may control sample size. So for example, you may find that you decide to just simply break up your sample based on pre-existing numbers. So let's say you're using GPA. You might decide to do D's, C's, B's, and A's. Well, you find that there's very few people in the D's, but at least they're relatively equal across your other conditions. That would still be fine. But you may find actually that you have differences between each block, but also you have that problem that there are only people in the D condition in your control group, but not your actual treatment group. Again, we're looking at one of the predictors then to ask this question: are the control units and the treatment groups comparable across those blocks? At which point you may decide, instead of A, B, C, and D, you may decide anyone below a 75%, 75 to 90%, 90 and above might be an example. So again, we can redefine the cut points for making this categorical decision on how we break up covariates. So again, here's another quick just blocking sample. And again, in this case, we're not making the argument that the first level, that low attentive Albert is the same as low attentive MH. We're simply saying that the people that have a low attentiveness probably have a different coffee consumption than those people with a high attentiveness. So we're going to measure attentiveness, and instead of using it as a continuous variable, we're going to use it as a blocking variable. In this case, a two-level one. We're going to create a high and low category. And before we ever look at the effects of individuals on their coffee consumption from control to treatment, we're first going to allow the attentiveness, low versus high, to account for a relationship with the outcome, coffee consumption. We're going to measure it and we're going to remove it. And then we're going to ask, beyond that, is there a difference between our treatment and control in coffee consumption? So basically what happens if we look at this in SPSS, and often we may want to be doing this, is actually asking the question, what would it look like without the covariate? What does it look like with the covariate? So for example, we might find that our treatment with no covariates included in the model, now again, we've measured them, we simply haven't included them, is not significant. We have a fair amount of error there. Our error mean squared is 7.6. Our treatment is 14. 14 divided by 7.6 is 1.84. P-value 0.20. However, if we look at the treatment, if the treatment is truly uniquely associated with the outcome, coffee consumption, and attention is only related to the outcome and not treatment, we're not going to find treatment changes. Treatment should still be about the same F. Mean squares of error are not F, but the mean square is still 14. However, now attention has mean square of error. The interaction between treatment and attention has a mean square error. And finally, there's less left for the error. So error now is 2.25 because we've accounted for more of what's going on in the model beyond the effect size. So in this case, now that treatment with the same data is statistically significant. And that's really what we're trying to do with a covariate, whether it's blocking or continuous. So computing the ANCOVA, when the covariate is continuous, an ANCOVA is simply computed by comparing the regression equations that measure the relationship between the covariate and the outcome variable. In other words, theoretically, it doesn't change. One factor and two factor levels, and again, we can have covariates in any type of ANOVA. It can be a covariate in a between subjects ANOVA. It can be a covariate in a within subjects ANOVA. It can be a covariate within a factorial ANOVA. And it simply compares the predictability of the outcome score with the covariate. And basically the null hypothesis is that it has no effect, and that the alternative hypothesis is that there is separate prediction equations for each level. In other words, if we look at the different levels, or if we look at the different continuous relationships, removing that variance actually gives us a clearer picture. So for example, our null hypothesis predicts post-test from pre-test scores. Our alternative hypothesis is we predict those post-test scores for those in the treatment condition and for those in the control group. So this is again an example of a very straightforward, very simple version of blocking, and I want to walk through kind of visually what's happening. So again, I've got a pre-test and a post-test. But I also have a blocking variable, and that is House of Hogwarts. So we've got Gryffindor and we've got Slytherin. So we've got the pre-test and post-test scores of everyone listed in pink, which is in Gryffindor, and we've got the pre-test and post-test scores of everyone in Slytherin, which is listed in blue. Now again, we're going to use the covariate to basically block them. We're going to account for the differences between houses before we actually look for the true difference between pre-test and post-test. Now, if we did not actually use this blocking variable, if we simply looked at pre-test versus post-test, what we would see would look something like this. So you can see there is a relationship looking at pre-test and post-test, but there's also a fair amount of error going on. In other words, the two lines, the dots are not necessarily very close to the line at all points. So again, if we're just looking at the relationship between these two, we see that if we're not accounting for house, we've got a fair amount of error in there. But what happens when we block it out and ask, what does the relationship look like for Slytherin, and what does the relationship look like for Gryffindor? And we find this relationship. And notice there's a lot less error. And this is how an ANCOVA, when done right, when a covariate, will allow us to really look at the picture. The relationship is actually a very strong relationship between pre-test and post-test once you've accounted for the differences between the two houses. So final thoughts, when should I treat a blocking variable as a covariate? And again, blocking simply refers to a categorical covariate. There's really not much of a difference in what's happening mathematically, whether it's a categorical or a continuous, though there is a little bit different in how we're actually calculating those numbers. The biggest thing is what is your research question? if your research question, if you have a hypothesis about that variable, it's a predictor. If you do not have a hypothesis about that variable and you expect it to be related to your outcome but not your predictors, then it very possibly is a covariate. After accounting for attention's effect on outcome, what is the relationship between treatment and outcome compared to how does attention affect outcome? Also recognize that if you're wanting to look at the interaction, for example, between your treatment and control and attentiveness, again, we're not looking at a covariate then. You have an interactional hypothesis. You can't have hypotheses about a covariate. The covariate has to be treated simply as noise. And again, covariates can be added, and notice there's an S there. You can have multiple covariates and can be added to any form of ANOVA with one or several factors. The interpretations are very similar. They simply become a little more complex.